Perfect.
Okay, perfect.
We got it.
Thank you. So thank you everyone to join the colloquium of ICF. And so today we have the pleasure to have the Dr. Nicolas Sisourat, who is associate professor in the Laboratoire de Chimie, Physique, Matière, Rayonnement. So basically in English is physical chemistry, matter and radiation. So in the University Pierre and Marie Curie in Paris, which is known as the Sorbonne universities right now. And so Nicolas obtained his PhD in 2008 under the supervision of Professor Alain Dubois, so in the same university, and over the theoretical study of interferences effect in ion atom and ion molecules collisions. And so after that, he moved to postdocs in Heidelberg University, and after that, go back in France and get the position finally after another. So at this laboratory as associate professor. And so Nicolas has a very nice career in researches because at the same time to teaching a lot, mm-hmm. he also produced a lot of papers, more than 80 papers in international peer-reviewed journals. And so it's a very nice, and he gets some awards for these reasons, and especially the Prix Aimé Coton in France, which is a pretty well-known one. And so we have really the pleasure to receive you today. And so you will talk about the electron attachments to cations in water by Interatomic Coulombic Electron Capture. So it's a real pleasure, and so you can start when you want.
Okay, thank you, Sebastian. So good morning, everyone. Even though I'm closer from dinner than breakfast, I would like first to thank Remy and Sebastian for the invitation and for organizing this colloquium. I understood that it's a pretty broad audience, so I try to keep the presentation short and simple. Sorry, but if you have any question during the talk, if I'm not clear, just don't hesitate to stop or to ask on the chat. I try to have a look from time to time, see if there are questions. So really, don't hesitate to stop me anytime. Okay, so what I'm gonna talk about is the interatomic Coulombic electron capture. It's an electron attachment process. So an electron comes, is attached to a molecule, and this is a standard process. It happens in many physical, in materials, in radiobiology, in astrochemistry and astrophysics. So it's very general. But here I want to talk to a really specific mechanism that was discovered about 10 years ago. And so that's this interparticle Coulombic electron capture. Just for simplicity, I'm going to use this acronym, which is ICEC. So when I talk about ICEC, that's this mechanism. Okay. So here's the outline of the talk. So it's first I want to present what is ICEC, what's the difference between ICEC and a normal or standard electron attachment. I'm going to quickly talk about the method that I use to study it. And then I'll give you a few examples of systems that we have studied in the last few years. So can I have the next slide? Okay, so as I said, an electron can come and attach to a molecule, an atom, quantum dot, but this electron comes with a kinetic energy, and somehow it needs to release this energy. And a standard way to do it is by radiative attachment. So the electron comes, and this excess energy is is released by a photon. So that's what you see in the first drawing, okay, on the upper one. But Cederbaum and co-workers in 2009 and 2010, they predicted that if this ion or these atoms or molecules or quantum dots as some neighbors, there is a new mechanism. The electron can come, attach to the system, but then there is no photon emitted. The energy is transferred to the neighbor, and the neighbor is ionized. So it emits another electrons with a different kinetic energy. So that's a different mechanism for an electron attachment. And they have shown that it's usually it dominates the radiative attachment. So whenever this acceptor system, the system where the electrons is captured as an environment, ICEC will take place and will be the dominant one. So yeah, there are several kinds of ICEC mechanism. So as I said, the simplest one is the electron comes attached to A, the energy is transferred and emit B. So you end up with A minus and B plus, and another electrons in the continuum. Okay. It can capture in the ground state of A, but it can also capture in the excited state of A. So that's the second, the lower drawing here. So it captures in a higher orbital. So you end up with A minus excited, and then many things can happen. It can release a photon, it can vibrate, so many things. So those two things is what we call the direct mechanism of ICEC. But then there are other ways also to do it. So there can be a resonant mechanism. So the electron is attached, but instead of ionizing the B molecule, so the acceptor molecule, then you first excite it, and then this excited state can emit the photon. So that's what we call the resonant mechanism. And again, it can happen from the ground state of A. So that's the upper drawing, but it can also happen in an excited state of A. So you get even more energy and you can excite even more B. Okay. And you can excite B so much that actually it can ionize it. Okay. Those two mechanisms, that's what we call the resonant mechanism. And last mechanism I want to say is that, so the electron comes, it attaches, but it doesn't release the energy right away. What it does is that it excites another electrons from A. So you get an excited A minus state. And then this excited state can relax, transfer the energy of B and ionize. So then you have a two-step. For first, an excitation of A, and then you have a release of the energy. So then you have some kind of resonances. You have a lifetime now that takes place before ionizing B. And again, you can have doubly excited states using the lowest orbitals or a higher one. And depending on the incoming photon energy, the different mechanism can play a role. Okay. So that's roughly what is ICEC, and with a simple picture of them, the different kind of mechanism that it can take place. So the ICEC process was predicted from theory. So far, I should say that there is no experiment. We are hoping that there will be experiment soon in the near future. I'm applying here and there to have beam time in several places to try to measure ICEC. Even though I'm a theoretician, I'm trying to do the experiment myself too. But there are also groups involved. So I hope that in the near future we'll have some results, some experimental results, some demonstration. Anyway, so after this demonstration, there was a lot of study by the group of Annika in Berlin and Federico in Cordoba in Argentina, but they are focused mostly on ICEC in quantum dots. The good thing with quantum dots is that they can use numerically exact propagation using several simple models. So they basically use MCTDH to do a fully numerical calculation, and they have shown that ICEC can also take place in quantum dots, and they have studied all these different mechanisms and show that it's dominant compared to radiative attachment. I just wanted to mention that there is this works, and there are really plenty, and it's interesting, but I'm not going to focus on that. I'm going to talk about ICEC in molecular system. Okay. So the ICEC process was first, how to say, predicted using an asymptotic formula. So basically what Laurent Sederholm and co-workers did is that they assumed that the acceptor and the donor, they are far from each other and far enough that you can neglect the overlap. If you do that, you can derive by hand the ICEC cross-section. Okay, so the cross-section for electron attachment due to ICEC mechanism. And the formula is given here. So you have some constant, and then you have so let's take the example of neon plus helium. Okay, so the electron attached to neon plus, and the energy is transferred to helium, which is then ionized. Okay. Then the distance between neon plus and helium is this capital R. So the ICEC cross-section is given by the photoionization cross-section of neon at the incoming energy, so that's this E, times the photon energy, the photoionization cross-section of helium at the outgoing electron energy. And those cross-sections, they are divided by R to the 6th, so the distance between the two atoms to the power of 6 times the energy exchange between the donor and the acceptor, so between the neon and the helium square. Okay, so it's very nice because then we have an analytical formula that we can apply. We know the cross-section for photoionization of neon and helium, and we can work out that. The issue is that it works only, it's valid only if the two atoms are far from each other. So that's the initial assumptions that we make. We say, okay, there is no overlap. Then the question I had was, what happens if they do overlap? Because actually at the equilibrium distance between the neon and helium, in real life, they do overlap. And so we know that this formula is not valid anymore, but we would like to know, does it give us an upper limit or lower limit? How is it? So then we needed to do a fully ab initio calculation where the overlap and the electron correlation and everything is included. And to do that, we use, can I see the next slide? Yeah, to compute that, we use the R matrix method. If you just give me a minute, I will just walk to start the light in my office because it's switched off and it's dark. Okay, sorry. So the R matrix is an ab initio method that it was developed in the 80s, and it's a very general method. You can treat electron collision with atoms, molecules. It works also for positron and so on. The idea is that you separate the space of the electrons into regions. The inner region where all the electrons are included. So the correlation between the incoming electron and the electron of the target, so what I call the targets would be this neon plus helium, okay? All these electronic correlation, these are included in the inner region, okay? In the outer region, where we assume that the electrons are far from each other and you can neglect the correlation. So then in the outer region, we treat just a single electron, so either the incoming or the outgoing electron, okay, moving in the field of the other electrons, in the mean field of the other electrons. So the wave function in the inner region is written here. That's the first formula. I'm not going to go too much into detail in this, but it's basically a configuration interaction method. So if you are familiar with quantum chemistry, it's the simplest, I would say, post-Hartree-Fock method, okay? And the correlation is included through CI. And we can do at several levels, including more and more correlation. But it's a let's say a technical detail. What you should keep in mind is that the correlation is included in the region, not in the outer region. And the R matrix is the boundary condition between the inner and the outer. And from the solution in the inner region, we compute the wave function in the outer region, and then we just propagate the wave function outwards, and then we do a simple scattering. I mean, it's standard scattering theory. We analyze the S matrix, and from the S matrix, we get the cross section. Okay. If you're not familiar with quantum chemistry or scattering theory, in a nutshell, it's just that R matrix is an ab initio method. It includes electronic correlation and the overlap between the acceptor and the donor. Okay, so it goes beyond this asymptotic formula. Okay, so then we computed the ICEC cross section for neon plus and helium, and we fixed the distance between neon plus and helium to 4 atomic units. So it's roughly the equilibrium distance between neon plus and helium in the dimer, in this van der Waals dimer. Okay. And then, so here on the figure, you have the ICEC cross section in megabarn as a function of the electron energy, of the incoming electron energy. The black line, that's the ab initio. So that's the result coming from the R matrix. And the red dashed line, that's the formula, this asymptotic formula where we neglect the overlap between the two atoms. And what you see is that the ICEC cross-section is even more, it's stronger than we anticipated. It's almost 2 orders of magnitude larger than the asymptotic formula. So the fact that the atoms can overlap, it increased by almost 2 orders of magnitude the cross-section for ICEC. So ICEC is really by far the dominant electron attachment mechanism for neon plus in an environment. Okay. Then we thought, okay, at the equilibrium distance, with the asymptotic formula give us just a very low limit of the ICEC cross section. But we were wondering when this asymptotic formula becomes valid, when we can start to neglect this overlap. So what we did is that now we look at a fixed electron energy. So in the upper panel here, that's the ICEC cross section for an incoming electron of 5 eV. And in the lower panel, it's for the electron energy of 10 eV. Okay. And now what I show is the ICEC cross section as a function of the distance between neon plus and helium. Okay. And again, the dots are the ab initio, so that's the result from the R matrix. And the lines are this asymptotic formula. And what you see is that below 7 atomic units, the ab initio ICEC is stronger than anticipated. So this overlap between neon plus and helium really just increase the ICEC efficiency. And then from 7 upwards, then basically we can neglect the overlap and the asymptotic formula is correct. Okay. So here we focus, so far we focus on a single dimer. So we have neon plus and just 1 helium atoms. But what happens if you put more helium atoms around? Unfortunately, we cannot do it fully ab initio because the R matrix is kind of demanding method. So we couldn't put a lot of helium atom. But if you use this asymptotic formula, you can show that the ICEC cross section is linearly proportional to the number of neighbors. So the ICEC cross section is the sum of the ICEC cross section for this pair plus this pair plus this pair plus this pair and so on. But then we were wondering, this pairwise approximation that comes from this asymptotic formula, is it correct when the 2 atoms are close from to each other? So what we did is that with the R matrix, we could compute a trimer. So we could compute ICEC where neon plus is in the center of the two helium atoms. Okay? So we computed the ICEC cross-section for this system, and we divided by the ICEC cross-section for just the dimer, for just one neighbors, neon plus helium. And if the pairwise approximation is valid, then we expect a ratio of 2, because we have 2 more helium compared to the dimer. And the data are shown here, so that this ratio is a function of the distance for 2 incoming energy, 5 and 10 eV. Okay, and what you see is that it's not really 2, but it's, let's say, around 2. So we were pretty happy to see that. And now we can use this pairwise approximation and the data from the R matrix calculation to compute the ICEC cross-section for a larger system. Okay, and this is what we did in the next slide. So now we consider neon plus in a larger helium cluster where we have 20 helium cluster in between. Okay, so what we did is that we took the Monte Carlo wave function of neon plus helium 20, and then we computed what we call the electron energy loss. Okay, so that's the energy lost by an electron coming and going through this cross section. No, sorry, going through this system. And if the electron doesn't lose any energy, so that's elastic collision, then you have a peak at 0 eV. Okay, so here's the cross section as a function of this energy loss, and so the elastic peak is at 0 eV. If ICEC takes place, then the outgoing electron has lost about 3 eV compared to the incoming electron, and that's the peak that we see here at energy loss a bit above 3 eV. And again, I compared the ab initio with the asymptotic formula, and what you see is that, okay, ICEC is larger, it's more efficient than anticipated by the asymptotic formula. But also, if you compare the elastic peak, which is pretty big, the ICEC peak, this energy loss peak, is only about a factor of 2 lower. So the cross section, this 10 megabar, is pretty high. So even on the absolute scale, we think that ICEC is dominant and should be easy to measure. So if you can really send an electron into this system and so on and do this energy loss spectroscopy, you should see clearly this peak. Okay, but so far there was no experiment, so we hope that this will take place in near future. Okay, so now I'm going to talk about another system, so still ICEC, but in a system that is more related to biology or radiation damage. So is there any question about the neon plus helium case or ICEC so far?
No, for the moment.
It's all good? Okay, good. So now I will talk about another system where the acceptor, so the electron is attached to a cation, so it's H+. Okay, so the electron is attached to H+ to form hydrogen, and then the energy is transferred to water, and you ionize water plus. So it's really the same kind of, it's the same process, but now we're looking at water, which is a bit more complicated, but it's also more interesting for biology because water is the solvent of life, right? And there are plenty cations in our body. So knowing how this ICEC can change, how cations can be reduced and oxidized, that's also very important. So that's why we started to look at that. The other thing is that in the water molecule, you can ionize several orbitals. So you have 3 outer valence orbitals, which are B1, A1, and B2. So that's just the symmetry, it's not important. They have different energy, but you can ionize any of them depending on the incoming energy. Okay. And again, we use the R matrix calculation to compute the ICEC cross-section. So in the next slide, what you see is again the ICEC cross-section for different distance between H plus and the water molecule. So we look at large distances where you have 6, 8, and 10 angstrom. But just to be able to compare the cross-section, we multiply the cross-section by R to the 6, because we know that roughly the cross-section should decrease like 1 over R to the 6. So by multiplying it, we can compare all the distances together, okay, on the same scale, okay? So again, so you see this cross-section times R to the 6 as a function of the incoming electron energy. So in red, it's for 6 angstrom, black 8 angstrom, blue 10 angstrom. The green dots, that's the result from the virtual photon mechanism, okay? And the dotted or the square, the black square, that's for H plus neon, because it's isoelectronic of water, so we wanted to compare, but I'm not going to discuss it here. So what you see is that the virtual photon, so this asymptotic formula, it does a pretty good job to reproduce the ab initio cross-section, at least in the order of magnitude. But what you see is that in the ab initio data, you have structures, clear structures. Like, for example, you have a dip at 1.2 eV, and then you have some kind of peak and dip in between 2.5 and 4 EVs. And those look actually like Fano profile. Initially, when I saw that, I thought I made a mistake in the calculation. So I rechecked everything, and no, it is physical, and those are really Fano profiles that you see in the Fano in the cross section. So what do I mean by Fano profile? What I mean is that you have interference between two paths. So you have the direct mechanism, where the electrons attach to the cations, to H plus, to the proton, and the energy is directly released to ionized water. But you can also have a resonant mechanism where the electron attach to H plus, but that it doesn't ionize the water. It stays there, it's bonded, it's for a while, and then the energy is transferred and the water is emitted, okay? And we can imagine many kind of resonances like this, where the electron is trapped into this H water cluster before it actually ionized again, okay? And because you have those two paths, you can have interference between those two quantum paths, and those interference, they give rise to this Fano profile. Okay, and then we studied, we tried to study a bit more into detail what kind of resonances it is, and we identified three kind of reference resonances. So in the first one, which is with the black arrow at 1.2 eV, that's when the electron is captured by the cation and stayed there for a while. But we also found that there is some kind of ion pair resonance states. So by ion pair, I mean states where you form H minus and water plus, and then you have ICEC, or you can have H plus, H2O minus, and then you have ICEC. And so that's the red and the blue line. So there are several kind of resonances, and they have different behavior and different profile with respect to the distances. So it was a good surprise to see these Fano profiles. We didn't expect it, and I mean, it's a nice curiosity, I would say. It's a nice physical process, but it's also a way to control the ICEC cross section, because now we can decrease or increase the ICEC cross section by tuning the electron energy. So for us, it's also a mean for changing the ICEC cross-section and controlling the electron energy. Okay. And we also look at the branching ratio, because as I said, we can ionize the water in different orbitals, so A1, B1, and B2, and they have a different branching ratio. And this is what is shown here in the upper panel. So that's the branching ratio between, so that's the cross-section for ionizing in A1 or in B1 divided by the total cross-section. Okay, and this is shown as a function of the incoming electron energy. And you see that where you have these Fano profiles, the branching ratio change also. So it's also a mean for controlling how to ionize the water. Because let's say you use just a photon to ionize water. The branching ratio is given by this photoionization cross-section. And you cannot say, oh, I want more A1 or I want more B1. Okay, it's just given by the dipole approximation, and that's it. Here we can play a bit. We have some kind of control on which states we want to populate, which orbitals we want to ionize. Okay, so for example, if you hit the system with an electron of 1.2 eV, you will mostly ionize the A1. While if you are outside of this, it's a 50-50 cross-section. Okay. Okay, now I'm going to move to, again, another system or other system. So just any question so far?
In this description,
maybe I have one. Just what all the properties of water change as a solvent, for example, when it is ionized? So I know it's not directly what you are talking about, but you are talking about, the nice property of water, which is the main solvent for our understanding of how to make more complex molecules and this kind of stuff on the early period of Earth. And so I was wondering how it changed the property of as a solvent of water when it is ionized. Okay, yeah, it's a good question. Actually, there are chemists, they have spent a lot of time studying what happens if you ionize the water molecule. So a very dominant channel is that you form OH. You form a hydroxyl fragment. So it's a radical and it's very reactive. And that's why actually we get cancer, we get sore muscle when you work out and so on. It's because we create these radicals that start to mess up with our other molecules, proteins, and so on. So if you ionize water, this water cation, it will mostly dissociate in H plus and OH, and this OH will mess up with your body. Oh, okay. Thank you. Okay, so that's why you should eat clean and so on. So it will this anti-radical stuff that we're talking about in the food and so on. It actually tries to neutralize this OH, which is the most the worst radicals that we get in our body. Oh, okay. Thank you. Okay, so if there are no other questions. Sorry, we have a question from Umberto. Please, Umberto.
Thank you. Perhaps I missed this, but is this one proton against one water molecule, or is this in the liquid phase?
Okay. So far, it's just one proton and one water molecule. As I said, this R matrix calculation, it's very expensive. And we cannot even afford to put a second water molecule.
Okay, thank you.
It's too expensive. So right now, we're not really quantitative. We cannot say, okay, ICEC in water is like this, because that's only a model system. Actually, we studied this system just to get started, and then we got these Fano profiles, and then we were more interested in this fundamental process, so to understand the Fano profile. than really to look at the biology that is relevant. In the next examples, maybe I'll talk a bit more about the implication in biology.
Okay, thank you.
Okay, so
I think there is no more question. Yes.
okay, thank you. So far I showed you that, so I introduced ICEC. I told you that we need to use R matrix because with the ab initio, we see that ICEC is more than expected by the asymptotic formula. And the asymptotic formula cannot give us this Fano profile. So that's the bad point with the virtual photon. But it gives us at least a lower estimate of the ICEC cross-section, and we can apply to very complex system, which we cannot do with R matrix. So we decided that before going heavy with the R matrix, we're going to study more system with this asymptotic formula. We know it's not going to be fully quantitative, it's only semi-quantitative. We know we're going to miss all this Fano profile and so on, but at least it would give us some ideas if ICEC is important or not, for which system it's more important and so on. So it's more like a qualitative study that now we wanted to undergo using this asymptotic formula. Okay. So that's the first thing. Now forget about the R matrix, just the asymptotic formula. We neglect the overlap between the donor and the acceptor. Okay. And we're not going to talk about the ICEC cross-section anymore. We're going to talk about the ICEC radius. So as I showed you with this asymptotic formula, the cross-section for ICEC is proportional to 1/r⁶, right? With r the distance between the donor and the acceptor. But we can turn around this equation and say that and define a radius r, which is given by the ICEC cross-section, by the other cross-section. Okay, and that's the formula that is given here. So what I call the ICEC radius is this formula, and basically what it tells you is that at the distance of this ICEC radius, the ICEC efficiency is 50%. Okay, so if my system is at this ICEC radius, 50% of the electron attachment comes from ICEC. If the distance is below the ICEC radius, then ICEC is the dominant one. And below, then you have electron attachment, you have other processes that is dominant. Okay? So if you're familiar with this resonant energy transfer, so this Fred or Foster energy transfer, it's similar than the Foster radius for resonant energy transfer. Okay? If you're not, just remember, if the distance is below the ICEC radius, then ICEC dominates. Okay? And at the ICEC radius, you get 50-50. Okay? So then now we have a simple formula. And we can compare this ICEC radius to the distance, the typical distance between a cation and a water molecule in liquid water. Okay? So again, we're not going to be quantitative. We just want to compare if in liquid water, if you get a cation, is ICEC efficient or not. Okay? And so using this formula here, so in this table, we studied all those cations, so lithium plus, sodium plus, and potassium plus. So that's the most stable cations for alkaline atoms. And we also study alkalinous atoms or cations, barium 2 plus, magnesium 2 plus, and calcium 2 plus. This is the energy of the incoming electron where ICEC becomes possible. So because of the difference in the ionization potential of the cation and the water, for lithium plus to potassium plus, you need to come with the electron energy of about 7 to 8 eV. Okay? For beryllium and magnesium 2 plus, even a zero energy electron will undergo ICEC, so you don't need to bring any energy. And for calcium 2+, it's a bit different from the other alkalinized earth cations, that you do need to bring some energy, but little, like 1 eV. Okay, or 0.28 eV. Okay, and so that's the threshold energy. And then we compare this ICEC radius, or the maximum ICEC radius here, that's the column. Thanks, Remy, I see that you follow well, to the first hydration shell. So what I call the first hydration shell, it's the distance between a cation and the first water molecule in liquid water. Okay, and it's different depending on the different cations. Okay, so what you see is that this ICEC radius, it's much larger than the hydration shell. So clearly, ICEC would be important in water molecule. It's by far below the ICEC. The first water molecule in liquid water is closer to the cations than this ICEC radius. So it's going to be by far the most dominant one. Okay. Can I see? Okay. Now maybe it's a bit. It's a lot of data, so I'm going to focus. So here, what I see is this ICEC distance as a function of the incoming electron energy for several cations, and I'm going to focus only on the lithium plus case, which is the one in the upper left corner. Thanks, Remy. And you see several colors because when the incoming electron comes, it can be captured into the 2s of lithium, or the 2p, or 3s, or 3p, and so on. And this change as a function of the electron incoming energy. Okay. And if you look at the y-axis, but on the right side, you see R1 and R2. So that's the distance between lithium plus and the first water molecule, and so that's R1. And R2 is the distance between lithium plus and the second shell of water molecule. So the distant ones. Okay. And what you see is that the ICEC radius is always larger than R1 and R2. So ICEC can take place with the first shell, but also with the second one, and it can go actually up to the 7th shell because it's so efficient. Okay. And roughly speaking, you see the same trends for every cations. Okay. Can I see the next slide? Okay. And here, now I show exactly the same. Okay. So it's the ICEC cross-section, but not in nanometers, not in absolute scale, but I divide this ICEC radius by the distance between the cation and the first water molecule. And if you do that, then you can compare easily the different cations. And what you see is that, for example, the beryllium 2+ is very efficient, whatever the electron energy. So ICEC is dominant in the for beryllium 2+, so that's the most ICEC efficient cations. So if you want to ionize the water molecule, then you better put beryllium 2+ into your liquid. Okay. But if you come with a high energy, lithium does also a good job. And among all the system, I would say calcium is probably the worst case, even though it can go still to the 6, the shell up to 6 shell of water molecule on calcium 2+. So it's still pretty efficient. Okay. Of course, all this comes from the virtual photon approximation. And so we neglect all the interaction between the partners, and probably the pictures will be different if we do a fully ab initio calculation. But at least it gives us some insight on ICEC in real system, in real liquid system. And now what we want to do is look at it with our matrix. So we're not going to go to full liquid, but maybe we can try to add a bit more water molecules and maybe use some QMMM mixed quantum mechanic calculation with some models. Okay. And now it's just so some conclusion and perspective. So I hope that, I mean, the take-home message is that ICEC is a new and very efficient processes for electron attachment. So it's important because it can be used to control ionization and reduction reaction in matter. And our matrix is really the tool to study ICEC. We do need ab initio. So our matrix is expensive, but it's worth the effort. And this is what we're going to do next. So now we want to redo all these alkaline and alkalinized systems, but using our matrix. Another thing is that everything that we have done so far is that we fix the nuclei. So we assume that the donor and the acceptor do not move during the process. But we know that when the electron will come, it will start to polarize the system. So things will start to move, and the nuclear motion can have an impact on the ICEC cross-section. And this is what we want to study. So all those two perspectives, this is something we are already doing with my colleagues. So we have a French-German collaboration. So we are 4, and the funny thing is that we are all coming from Heidelberg. So at some point we were all in Heidelberg, where I met Remy, and now we decided to continue working on that. And so with that, I would like to thank you for your attention, and if you have any questions.
Thank you very much.
Thank you so much, Nicolas. It was a very nice talk.
Thank you. Just give me a sec. I'll switch on the light again.
Yes.
Since I mean it's an automatic light, and in the evening, because it's the evening for me, then it switches off very often, so it's very annoying. They don't want us to work during the night, so they do that.
That's typical French. So
Exactly.
please, do you have any questions, please? So you can raise your hands in the chat. So please, Umberto.
Okay, thank you. This is very interesting. Some colleagues and we have some experience in using a molecular dynamics, ab initio, well, Born-Oppenheimer molecular dynamics with small clusters of water surrounding cations. That is some 40 water molecules. And because the first and second hydration shells are included, the information is can be compared to experimental data on structure. And well, we haven't finished, but we have some study on the transfer, on proton transfer. So perhaps you don't need to do QMMM. You can do with directly a medium cluster. There's some 40 water molecules in the cation, and that will give you, I would expect that will give you the local behavior.
I understand what you're saying. I agree if we are interested in what happens after ICEC, but what I mean by QMMM, or it's really including also the ICEC processes, so the electron coming, attaching, and what happens when the electron it's still there, not after it left. And this, I don't think you can do it easily because we need our matrix, we need scattering theory.
Okay.
So, but as I said, I hope that there will be experiment in the near future, and one. I just applied to have beam time in a synchrotron in France to do this kind of experiment. And what we want to do is look at magnesium 2+ in water, and after ICEC you form magnesium plus and water plus. Okay, So we know that ICEC is very efficient. It will take place. What we don't know is what will happen if you put magnesium plus and water plus in with plenty of other water molecule, because now you have this cation, this repulsion between the ions, okay? And we don't know what will happen. Maybe there can be some charge transfer. Maybe there can be the water plus can fragment and form OH as our answer. Maybe it's different and so on. And maybe with dual method, we can study that. So that's, but it is after ICEC. But it would be really useful if we can do the experiment, and we need some simulation to understand the experiment. So thanks, and maybe I'll write to you someday.
Sure. I'm not at the university right now, but I will be there tomorrow early in the morning.
Well, the experiment will be done next year. I've applied last week. Then it goes to some referees and so on, and if it's accepted, it's for next year, because synchrotron are really big facilities, and it's not something like you have on your desk and you can do anytime. So it's really.
I see. Well,
thank you.
Thank you.
Remigio, por favor. Do you have a question, Remigio? So maybe your mic is turned
Yeah,
on.
yeah, you were right. My mic was off, so I was talking and sorry. Very nice talk, Nicolas. I like it a lot. It's really impressive word that you're using. One of the questions you answered at the end, when you, of course, know the field of my work, nuclear motion is something very interesting, but you said that you're doing this static approximation.
Yes.
However, from the theoretical point of view, let me move to one of the slides that you were presenting, just to make this clear. For example, in this case, the protons at a distance of with water molecule. In this case, what is the mechanism that you are assuming that selects that the electron is captured by the proton and not by the water? Because both processes could happen also. I mean, the electron could be captured by water and makes a negative H2O. So
yes.
in this case, there must be some assumption behind this approach.
No, actually, that's the good thing with the R matrix, is that everything is included. Okay.
So the main channel is the captured by in this case, the proton.
Yes. So, but everything is included, and this is why we have these Fano profiles. Without that, we wouldn't get it. Okay.
Yes.
But what the R matrix shows is that it's negligible. All the other channels, they are negligible, and ICEC is really the dominant one.
The dominant one. Now, from the experimental point of view, from the experimental point of view, in this case, having a proton immersed of water, the electron, it will neutralize very quickly, and particularly the dipole moment of water is very high. So the experiment, I think, would be very complicated to do in this case. Also because water, I am assuming, is not in the gas phase, it would be in the liquid phase. So that experiment in particular, I think it will be very tough. I'm not an experimentalist, but just looking at what colleagues have told me, it's not that simple. But neon and on neon plus on helium, that's something to be more realistic. And in that case, I can see that, of course, the dominant channel is the neutralization of neon because it's the charged ion, and it would be helium, the one that will try to lose the electron. So the ICEC it's very selective in that case, as you just pointed out. The method does include it. My last question, now that was a comment. My last question is, in your R matrix approach, are you using plane waves to describe the incoming electron, or you're using some kind of distorted wave approximation?
Okay. So about your comment, I fully agree with you. So what we suggest with the experimentalists is to do neon plus helium because it's the cleanest experiment one can think. Now for liquid water, we studied the proton because it's the simplest one from a theoretical point of view. But
Right.
really, for the experiment, I wouldn't suggest proton. I would suggest magnesium 2+.
Okay, good.
Okay, or all these cations that we studied later. Okay, because then those we know that they stay like this in water. If you put a proton in water, in liquid water, yeah, you would have neutralization and so on, but not these cations because they are stable. Okay.
Mhm.
Now about your question, no, we use B-spline to describe the continuum electron.
Oh, okay.
So we use B-spline, and really the R matrix is a non-perturbative method. It's a close coupling method. So compared to firstborn, it's not a firstborn or a distorted wave. It goes beyond that. It's not perturbative.
Okay.
So
that explains how you can treat the incoming electron and the outgoing electron, because
exactly. You don't have to you don't assume anything about the channels. You just put the channels in there, and then our matrix does the job for you.
Okay.
So it's heavy. That's heavy, of course, but at least you get in principle an exact answer.
And in this case, does vibration of the molecule play a role on the ICEC?
We want to know. That's my perspective.
Okay, so that means that these results are for ground state vibration, no vibration at all.
Yes, it's fixed. It's a yeah. But that's what we want to do now. So we're not going to do it with R matrix right away because it's really heavy, and we don't even know. We're not even sure how to do it. But we're going to do it on a simple system with MCTDH, where with MCTDH we can include the 2 electrons and some degrees of freedom for the vibration.
Okay. For our colleagues that are not in the field, MCCTH is multi-configuration of time-dependent Hartree-Fock, which is, I think, it's the way to go. And I will keep in touch to you because this system, these systems, lithium plus on water, H plus on water, I can do it with the electronuclear dynamics. And in that case, it would be interesting to see the 2 questions that I asked. What is the effect of the nuclear motion? And also the initial vibrational state of the molecule.
Okay, then we should definitely talk because you know Federico Ponte from.
No, I haven't met him.
Okay, so maybe someday we should have a chat with him. He's doing this MCTDH, so we're doing together, but he's really running the calculation, to be honest. And he has a model system where it would be nice to study with MCTH is nice, but it's limited to model system. But maybe with other methods like yours and so on, we can go beyond that and bridge the gap between R matrix and MCTDH. So
thanks.
Whenever you want to do that, just that will write to me.
Okay, sure. Thank you very much. This was a very nice talk.
Thanks, Remy. Thanks again for the invitation.
Umberto, please.
Thank you. I just wanted to mention that there is no such a thing as in liquid water as a proton surrounded by water molecules. It attaches to either one molecule, so there is what is called the eigen cation, or to 2 in the Sundel. And the process is very dynamic. It happens in very few picoseconds that the proton moves all around. And it produces very interesting phenomena, but it's very difficult to say where it is.
Again, I fully agree. I mean, we studied proton because it was just simpler for the R matrix calculation. But we're not claiming this is something one can do experimentally. Or in real life, it's not like this. That's clear. That's why then we moved to these other cations, because we wanted to be a bit more realistic, even though we cannot do R matrix. But really, the proton was just a model case for to understand how it works.
Yeah, well, there are also some charge transfer phenomena when water surrounds small ions. When it is close enough that it's not clear that the cation remains with all the, I mean, that the electron goes all the way to the water molecules. There is some sharing.
Yeah. This I agree. And
there are some. It's an involved phenomenon.
Yes, but the R matrix should take into account this kind of partial charge transfer and so on, this polarization and so on. I mean, in principle, if you put enough correlation, you should have it. So I hope that we'll see this kind of thing. Yeah.
Okay, thank you. This I found it very interesting. Thank you.
Thank you very much.
Thank you, Nicolas. So I have a last question. I'm really sorry. I know it's very late for you, but I'm very interested in that, and I don't know anything. So as you know, I'm in cosmology, and so we have something with lithium. And so I have a question. Do the results exist for ICEC study considering lithium with the dihydrogen molecule? And so do you think that you can have at this kind of level modifications in what we can consider with just ionization process of the lithium, but considering the ICEC process?
So there is no work on this system, lithium plus H2. It should be pretty okay to do with the R matrix calculation. So I've done lithium plus with helium because I think it's also relevant in astrochemistry. But not with H2. This is something that can be done, and definitely it will affect the cross section for ionizing H2 or for neutralizing lithium.
Okay, thank you so much. Because we have a lithium program still to understand properly the nucleosynthesis, the primordial nucleosynthesis, in fact. So we have everything pretty well done, but with the observation in pristine system, we still have a disagreement with the lithium measurements. But in fact, I'm not sure this kind of stuff is taken into account. So I just discovered that it exists. So I will take a look on the existing papers to see what they do. But it should be very interesting to see if there is some modifications on the theoretical part, taking into account ICEC.
Well, the thing is that you need to have these low energy electrons, right? So I'm not a cosmologist, but I feel that I guess in those places, that's not what you see most. It's not free electrons. It's more like photons, UV photons, or.
In fact, In fact, where you are supposed to take a look is pretty far away from the UV sources. That's exactly why it's very hard, because if you have UV photons, by definition, you have a new nucleosynthesis from the stars or astrophysical objects. So what you want is to have a look to pristine systems that are pretty untouched by astrophysical sources and UV productions in particular. So I think in this case, in fact, just by the collapse of small structures, you have pretty free electrons there. And with so high energy, so it should be very interesting to take a look. So if one day you have some H2 lithium or this kind of stuff, ICEC, I think it would be very interesting to take a look on that for a cosmologist.
Okay, it's good to know. It's good to know. I'm always up to and those should be pretty easy to do. So maybe I'll have a PhD student starting in October. And I had a plan to start on another system, but maybe it's a good start because it's simple and it can do the calculation. Maybe okay.
Thank you. Thank you so much for your talk. It was very, very interesting. Even for me, who is very far away from this topic.
Okay. Well, thank you very much. And hopefully next time I can come and give the talk. When I have result on lithium plus H2 and on then I'll come and show you that there. Okay.
Perfect. Thank you so much, Nicolas. Thank you so much for your time. I know it's very late.
It's all right. So have a good day.
You too. Have a good evening. Thank you for.
And thank you again.
Thanks.
Bye.
Thank you, everyone, to join.
Bye. Goodbye, everyone.